Welcome to Pomodoro Joe for Monday, February 27th, 2023. Today we're doing LeetCode problem 427, construct quad tree. This is a medium problem. Whoa, this is a long one. All right, let's see here. Given a n by n matrix,
grid of zeros and ones only, we want to represent the grid with a quad tree.
Just gonna skip ahead a little bit. This is a lot to read. Check out the link in the description for more. You can read this entire thing on your own. For now, we're just gonna jump over to the wiki to learn a little bit more about quad trees. If you want to know more about the quad tree, you can refer to the wiki. Let's check out the wiki. Okay, quad trees. Oh, so these are like, if you've done any 3D graphics or video game programming, this is like an octree. So you have a grid, in this case it's 2 dimensions, and you can split it evenly into 4 subgrids, and then each of those subgrids you can split evenly into 4 subgrids. So essentially these are going to have to be some power of 2. And you can use it for things like resolving a compressed image. Okay, pretty cool. All right, quad tree format. The output represents the serialized format. Yeah, even more reading here, but we're going to skip ahead and I'll just summarize the whole thing. Okay, I'm just going to summarize this one really quick because this is a lot to read, but basically we are given a 2-dimensional array grid. Looks like this. Actually, I'll break it down here. It looks like this. So we have a 2-dimensional array. In the array, it only has ones or zeros as the values of each element. Now we're going to build a quad tree from this 2-dimensional array. And the quad tree has the following properties. It's very similar to a binary tree, but rather than each node having only 2 children, a quad tree, every node has 4 children. And each of the 4 children represents either top left, top right, bottom left, or bottom right. So in this grid, this whole thing will have 1 root node, and then it will have 4 children, each representing top left, top right, bottom left, or bottom right. And the way that the leaf nodes work, if all of the values in a quadrant are the same, then the value for that node is the value that's in that quadrant, and isLeaf will be true only if all the values are the same. If the values are different, isLeaf will be false, and then the value doesn't really matter. Okay, it's a lot to absorb. I recommend you go check this one out. I'll leave a link in the description. You can read through this at your leisure, and then we can jump into solving this problem. All right, that's 427, construct quad tree. Okay, we'll put 25 minutes on the Pomodoro timer and get started. So this one, it pretty much tells you how you solve it right here. If the current grid has all the same value, then you set isLeaf to true, and you set the value to the value of the grid. If the grid has different values, then you set isLeaf to false, and you recurse for all the subgrids. Okay, so that's pretty much it. All right, for this one, we're going recursive. So we'll just follow the instructions in this description here, and we'll see if we can solve this problem. I think because of the way this grid is stored, it will be easier just to use the coordinates of the top left and bottom right corners of our grid in question. So we'll have a helper function here. So we have construct recurse. And for this, we'll take the top left and bottom right corners of the grid. So we'll have an x1, y1, and x2, y2. And this will return a node. Let's see, if our grid is only 1 square wide, it only has 1 element in it, then we can just return a node. So if x1 is equal to x2, that means there is only 1 element in this grid, then we'll just return a node. And the node's value will equal whatever the element's value is. So that's going to be grid. And we do y first because rows come first and then columns. So it'll be y1 and x1. And isLeaf will be true, because this is the only element, it has to be a leaf. So that's our base case for one element. If we have more than one element, we don't know if this is a leaf or not. We would have to check every value in this grid to see if it is a leaf. So we can do that, or we can just go through and find all of the child nodes and figure out if those are leaves, and if they are, then this could be a leaf too. So let's make this easier on ourselves and just find the child nodes. And then we can come back and maybe optimize by just checking to see if this node's a leaf right here. I'll just make a note. At this point, we're going to have to go through and find all the child nodes. So to find the child nodes, we have to find the dimension of this grid because we don't know it right away. So n will be, let's see, if we've got a 1 by 1 grid or a 2 by 2 grid, if we have 1 by 1, our x1 and x2 will be the same as we've already determined here. So that means our width will be, let's see, x2 minus x1 plus 1. Because, so if we had a 1 by 1 grid, x1 and x2 are both 0, this would be 0, but our n will be length 1. If we have a 2 by 2 grid, then we have x1 is 0, x2 will be 0, 1, so 1 minus 0, so we have to add 1. All right, so we add 1 to get our dimension here. So this tells us the dimension of our current grid. Now we're splitting this grid into 4 subgrids, so we need to find our half dimension essentially. So half will be n integer divided by 2. All right, and now we have our top left, top right, bottom left, bottom right. So let's find those. So let's see, the top left, we're going to do this construct recurse. So we're going to make our recursive call. We have our base case here. Now we have our recursive call, and we will have to do one recursive call for each quadrant. And let's see, now our top left quadrant, so if we're looking at this example here, this one is our top left quadrant, so our x and y ones are the same. So we just keep x1 and y1. But then our x2 will be x1 plus 1/2. And our y2 will be y1 plus 1/2. All right, and I think we have to do the same for bottom right. So we'll have to do all of these, top left, top right, bottom left, bottom right, and we'll have to figure out its coordinates. So top left, top right, bottom left, bottom right. Okay, so let's see. Our top right then, we will have x1 plus 1/2 as the starting point. Now it looks like these are going to be starting and ending at the same place. Like this goes to x1 and a half, and this starts to x1 plus 1/2. So I think we actually want to go to just before the halfway point. So I'm going to speed through this really quick. This was just finding the top left, bottom right coordinates of each one of these 4 quads. It took a little bit of time. It's just simple math, but I wanted to make sure I got it right, so it took a little bit of time. If you're interested in seeing the actual thought process behind this, leave a comment and maybe I'll post that later at regular speed. If not, that's totally fine. You can check out the final code. There's a link in the description. It takes you to my GitHub. You can check out this code on your own, read through it, see if it makes sense. Wow, this is taking so long. I'm running out of things to say in the voiceover. So yeah, that's it. And then finally, x1 plus 1/2, y1 plus 1/2, x2, y2. Okay, oh man, this is tricky. So getting these coordinates right is definitely tricky. So let's see here. Now that we have all of our other nodes, we're going to have to figure out if this node is a leaf node based on their return values. So let's see, I'm going to have some like total value. And we'll just say that's the sum of all their values. So this will just say if we have 0, we have all zeros. If we have 4, we have all ones. If we have anything else, these are a mix of zeros and ones. Let's see, is leaf? Well, I guess this could be a leaf if all of the other nodes are also leaf nodes. They consist of just zeros and ones. So let's check. Okay, finally we can have our own node. So this node will be some new node, and we'll say this node's value will equal, I guess, the total value divided by 4. So this will basically tell us whether or not we have zeros or ones, but it doesn't matter unless this is a leaf node. This will be a leaf node if all the children are leaf nodes and this value is either 0 or 1. So this might seem a little bit strange here. So this is basically saying we need to check the total value. I need to make this called total val. So we check the sum of all of the child nodes. And if that sum is 0, that means all the child nodes have 0 as their value. And if we check that they're leaves, then we can say confidently that this node could be a leaf with a value of 0. If all the child nodes are leaves, but their values range somewhere between 0 and 4, then we can't confidently say that this node is going to be a leaf as well. And finally, if this node is leaf is equal to false, so this is not a leaf, then we need to set all of its child nodes. So node dot, let's see, we got top left, node dot top right, node dot bottom left, and node dot bottom right. And we will return this node. Whew, that's a lot. So this is our recursive algorithm, and we still need to call it. So in the outer function, we will return this recursive function. That's going to be, let's see, we need to get our x1, y1, and x2, y2. Well, our x1 and y1 will be 0. We already know that, so that's pretty easy. We can say 0, 0. But now our y2 and x2, we need to get the length of our grid. So our grid length, the length of our grid, and we will need to subtract 1 to get the final index of our grid. Okay, I think we got this all wrapped up. Let's give this a shot and see how we do. Let's see, I must have, oh, got this extra comma in here. Any other extra commas? This was by far the trickiest part, is figuring out all of these coordinates. Okay, let's see if that fixes it. Should be equals. There we go. So many typos. And of course I get the wrong answer, because why not? So this node will only be a leaf if all the child nodes are leaves, and the total value is either 0 or 4, not 1. There we go. All right, this was a rough one, folks. Let's submit this and see how we do. Oh, not too bad. So we do pass. Not a great algorithm. We beat 49% for runtime and 6% for memory. So not super great. We have about 6 minutes left on the Pomodoro here. 5 minutes. Let's see if we can speed this up at all. So one thing here is this optimization. Can we just say this thing is a leaf or not right off the bat? Let's try that. So let's see. We'll set a target value equal to our grid at this x1, y1. Again, we have to do y first, y1, x1. So now we're just going to go through from y1 or x1 to x2, y1 to y2, and check this target. And if they're all the same target, then we can confidently say that this is a leaf and we can do an early return. Let's see, we'll do y first. So we'll just assume it's a leaf, and then we'll set it to false if we ever get something that's not the target. So let's do this. And let's make sure we break out here too. Okay, so if we break out of both of those, and we can say if is leaf, then we can just return early. Okay, let's try this. Looks like I'm getting the wrong answer. Maybe I'm returning too early. This is not inclusive. Okay, let's try that. With 1 minute to go, see if we can beat 90%. Oh, so close. 89.2% for runtime, 20% for memory. That's as good as I got for today. Sorry, folks, but thank you for watching. Hope you enjoyed this. Hope you had fun. Hope you learned something. Check the links in the description. Please like if you enjoyed this. Check out my other videos because this one is definitely not my best. Okay, folks, that's all for me today. Hope you enjoyed it. Hope you had fun. Please write better code than I.